Yes, hi. My name is Marko Krco. I'm actually from the National Radio Astronomical Observatories of the Chinese Academy of Science. Obviously, I'm Chinese. Namely, I'm the FAST Senior Operations Scientist. And I've been working there since we began commissioning in 2016. Now I've noticed today, and there's a lot of talk about interferometers and many new and exciting telescopes. FAST is a little bit outside of that in that it is still a giant collecting surface, a single giant collecting surface. Now, there's actually quite a bit of discussion about both big data. And we're dealing with huge volumes of data now. We've been observing at full speed for 3 years now. We're actually regularly collecting, about 500 terabytes a day. And it's our biggest bottleneck right now in actually getting science results out. We've gone back to treating our graduate students like mules and having them carry hard drives and whatnot, because our data requirements turned out to be much larger than what we had actually planned, even just from a few years ago. But in this talk, it's such a short talk, I really can't discuss everything. But what I would like to do is give a little bit of an introduction, because I know many of you probably do not know much about FAST. I'd also like to talk about what it is that we're doing, our largest current project. And I would like to discuss our newest technology, which has actually enabled us to conduct the first fully commensal survey. So this means that while we are observing with the telescope, we are conducting 5 different projects simultaneously, which are all using the same data. So instead of doing 5 surveys one by one, we're doing all 5 of them at the same time. So I'll try and make this quick. So FAST, I'm sure you know, it's pretty big. So it's a 500-meter telescope. It's the largest single aperture in the world, filled aperture. Now, there's a lot of comparisons to Arecibo. You would be mistaken to think that it's a larger Arecibo. There's actually quite a few different characteristics between the telescopes. For example, we have an active surface that shapes into a parabola as we need it. But the biggest difference, which really translates into scientific results, is that Arecibo used to have that big honking structure, 220-ton structure at the feed, whereas our structure, you probably cannot even see it in that picture, but it's only 30 tons and only about 7 meters across. So that means that we actually get much cleaner baselines. Our 1 megahertz ripple, if you're familiar with that, is a much simpler thing to deal with. And I myself worked at Arecibo for many years, and there's quite a difference between them. So, as with every new telescope, the first things you want to do is you want to use it to open up new doors. So this means, generally conducting large surveys. And I'm sure that SKA will do that, Meerkat is doing that. We wanted to do that as well. The only thing is, though, that in order to properly observe, to do drift scans of the whole FAST sky, that's about an 11,000-hour project. And so we had Galactic H1 people wanting to do it, Extra-galactic HI people wanting to do it, Pulsar people, FRB people, Continuum surveys. Everybody wanted to do it. Instead, we decided to do them all at once. And that is this Commensal Radio Astronomy Fast Telescope Survey, CRAFTS. We've actually been doing this for 3 years now. We've been observing. We've already covered about 3,000 hours of observing time. This is the Pulsar people, they've managed to get their results out first because they don't really need to calibrate them as well. But now we're actually coming out with spectral line results. as well, and maps, and I'll show you one in a moment. But the big thing here is that this idea of commensality is not at all new. So I think the first people who actually tried it were the people at Parkes once they got their multi-beam. But the GBT tried it, Effelsberg tried it, Arecibo tried it, and none of them were actually able to achieve it for a variety of reasons. But the biggest hurdle was actually a technological one. And this is, I think, probably the most important point I'd like to get across in this talk. So why is it so difficult to do commensal surveys? I mean, we're collecting the photons, right? And we can record them, and nowadays our backends are such that we can record pretty much however many channels we want, whatever time resolution we want. So if we can record the data, why can't pulsar people and spectral line people use it? Well, the reason is that the spectral line people, they require for their flux calibrations to be much more precise than the pulsar people. So we require a cal. So it's a noise diode which we fire periodically. It has a known signal strength, and we fire it in order to calibrate our signals. It's mostly to get rid of electronics gain fluctuations in our system. But that's a repeating signal in our signal path. So when pulsar people look at that, well, up in the top left, that's a test run that we did at Parkes back in 2017. What you see, so that's a signal from an observation where we tracked the pulsar for a couple of minutes, a known pulsar. And in black, you see what the Fourier power spectrum looks like with no noise diode. In red, you see what it looks like with a noise diode. And since, I don't know if you can quite tell the scales, but those peaks in red are about 6 orders of magnitude bigger than any signal. And there's definitely a strong pulsar in there. So this is why this couldn't work before. This was the biggest reason. But in this case, what we did was we fired the noise diode with a period of every 2 seconds. So, and then we noticed, well, that first peak starts at about half a hertz. And I'll try and make the long story short. What we decided to do was we decided to build a noise diode, which we could fire with a period of 200 microseconds. And so that's what we are doing now. And what it looks like is we're recording pulsar data at 100, actually it's 98, but let's call it 100 microseconds. And our noise diode is on for about 100 microseconds, and then it's off for 100 microseconds. So in the pulsar data, what you see one spectrum where the cal is on, one spectrum where it's off, and they are perfectly synchronized. So that it repeats even through hours and hours of observation. That required building different types of equipment, but it's actually all fairly simple once you get to it, and it's relatively cheap to implement at other observatories. But the end result is that we record pulsar data and spectral line data, as well as FRB data and continuum data and extra-galactic HI data, but we record all of this data, but only the pulsar data is actually able to see the noise diode, because the noise diode is turning on and off every 100 microseconds. You know, the spectral line folks, we get a spectrum every 0.2 seconds, so we don't see the noise diode at all. But what we've managed to do is we've managed to build our system in such a way that we preserve the signal path. All of those different projects and all of those different observations, they all go through exactly the same signal path. So we can actually calibrate the pulsar data and then simply scale up all of the other data to that. Now, this is actually on the right. There's a bit of a diagram about how this actually works. Believe it or not, that's the simplified version. But the end result is that we're actually able to conduct these types of observations. And this has been a huge boon for us. This CRAFTS survey, which is going to be an all-sky drift survey, it's going to take us 11,000 hours to complete. We still estimate that it'll probably take us until the end of this decade at least to finish it. But if not, it would take us 50 years to do it. And this technology, well, the new ultra-wideband at Parks, we've actually worked quite closely with them, so their new UWL is actually compatible with doing this kind of stuff. It's been built from the ground up to do this, just like our main 19 beam receiver, but it would actually be pretty easy to implement at other telescopes as well. And I would urge you, if you take anything from this talk, it's that this is now possible. There really is no technological reason, especially if you're building a new telescope, you're beginning a new survey. There's more problems in this than I can cover in a short talk, but the key point is that this is possible. Our paper is going to be out soon. It's on this. But you should be considering that if you're doing any large-scale surveys with Meerkat, SKA, or something like that, if you're going to design these systems, please keep in mind it's no longer necessary to do projects independently. Commensal observing is now doable. And I have only a few minutes, I think. So I'd like to just show you some results. So this is from the Galactic H1 part of the survey, and this is actually what I'm focused on mostly. The closest analog that we have to our survey is actually GALPHA. So that was the Arecibo Galactic Alpha survey. And so here's a map of Taurus, and this is actually, it's a little bit inverted, so this is actually the H1 narrow self-absorption in Taurus. So in the actual image is fast. The contours in red are fast, and in green are GALPHA. So the basic takeaway is that actually we've actually calibrated this data using this high cadence cal that we've been using, and it actually works. And in the bottom, I'm actually showing you a cube. This is our first data release. This is actually around the Orion Molecular Cloud Complex, but this is something like 600 square degrees of the sky. It's actually only about 8% of the data that we've collected so far. So our next data release is coming up now. It's actually quite a lot bigger than this. But why is this important? One, so with SKA coming up, look, the SKA is great. It's going to be huge. It's going to have a larger surface area than FAST, but it's not a single dish. So when it comes to doing especially galactic H1 astronomy, you need that zero spacing data. And what we're going to do is we're going to provide that zero spacing data that's going to be actually usable for SKA and Meerkat and others. But the biggest difference is that we're doing this at 0.5 kilohertz channels, and everybody else coming up is doing it at several kilohertz channels. So this map that we're making now, this is going to be the new lab survey, the new high 4 pi for the next several decades, because nobody's building. There isn't even a telescope on paper to do something like this better.
You should finish in about a minute.
Yeah, that's my last slide. This is actually just a backup slide in case my movie doesn't work, but I would just like to show you, this is actually the Orion Nebula. This right
you
here,
can use
that
thing as a laser pointer on top.
Yeah. Here we go. So that's the Orion Nebula, actually. This is the highest spatial resolution image from an actual single-dish telescope that we've ever been able to get, because Arecibo was not able to go down far, this far south. And yeah, I think that's about it. I should call it quits here. I would just like to say that we are actually accepting applications for observing time. Doesn't matter if you're Chinese or not. And we've actually, right now, I think in the last cycle, about 20% of our time went to international collaborators that were not at all connected with China. So we're completely open. And we also, if you have any questions, I'd be happy to answer them. Thank you.